Hello everyone, welcome to add-on. So now we are going to solve this question based on SFT and BMD, where as you can see, we have been given a beam E, let us call it EG, where E is a hinge support, G is a roller support, as we have been given some boundary condition like movements at C and E, sudden force at D, and UTL between EB and FG. So let us see how we can make the SFT and BMD of the following diagram. Firstly, we need to draw the FBD to get the support reactions, which is a support at A and G. Then we will find the shear forces at every point, and then we'll find the bending moments at every point. So that is how we'll go, because shear forces we will need to find the SFD and bending moment to make the VMD. So let us see how we can solve this. Firstly, we will draw the FBD as the first step suggests. So we have a beam A, B, C, D, E, F, G. Yeah. So we have a hinge support at A. So we will give two reaction forces here, which will be FAY and FAX at B. Between E and B, we have a UDL. So we need to convert that into a point load, which will be 50 into 200 Newton acting at the center of the UDL, which will be 100 acting at 1 meter from A and 1 meter from B, because the total length AV is 2 meter, as you can see in the figure. So the conversion of UDL is very easy. You just have to integrate K dx, which K is nothing but the magnitude of the UDL, which is 50 as given in the question, 0 to x, and the total integration of these becomes Kx. So x was the total distance of the UDL, which was 2. So 2 into 50 becomes 100 is the total magnitude. So this is the force magnitude, and it is acting at the center of the beam, center of the UDL, and it was 1 meter from A and 1 meter from B, because it was a rectangular load. So the center will be at the midpoint of the UDL. We have a moment at C, 800. We have a force of 500 at D. At E, we also have a moment, 1000, let us say. At G, we have a roller support, so there will be only one reaction, which is at GY. And we also need to convert this UDL, which is 100 into 200, acting at 1 meter from G and 1 meter from F. The distance between EF is given as 1. DE is given as 2.5. CD is given as 2.5. BC is given as 1. So yeah, let us see. This is what our FBD becomes with the distances given from the beam. So let us see how we can solve this. To solve this, we need to apply the 3 equilibrium condition, which is summation fx is 0, summation of fy is 0, and summation of movement at any point is 0. So summation of fx is 0. If you apply, you will get that fax, which is the only force in the horizontal direction, becomes 0. This is done. So we have summation fy 0, which will become that fay because of the reaction force at A, minus 100 because of the UDL, minus 500 because of the point force at D, minus 200 because of the UDL again, plus FGY will become 0. So we have FAY plus FGY as 800. This is our equation number 1. You can see that there are two variables, FAY and FGY, but only one equation. So you cannot solve this equation until you have a second equation, which will be coming from the movement condition. So we need to apply the movement condition now. We have a movement at any point throughout the beam is 0. So we can apply this condition at any point, E, B, C, D, E, F, G, whatever you want. But in our condition, we will be applying it at E, because FAY will then disappear because it is going through that point. The force is going through that point, so it will disappear. So we will have only FGY as a variable in your equation. So we will apply this condition at A. So we have a summation of movement at A is 0. Which will become 100 into 1 as the clockwise movement. So clockwise will take it as positive, and anti-clockwise will take it as negative for the movement. You can change this. If you want to take anti-clockwise as positive, you can do this. It won't affect your solution. We have a clockwise movement at C, which is 800. So we'll just add 800 here. It is a clockwise movement, so we have the given positive side. And we have point force at D, which is again going to generate a clockwise movement. So we have 500 into the total distance between A and D, which is 3 plus 2.5, which is 5.5. So 2.5 plus 3, which is 5.5. Minus 1000 because of the anti-clockwise movement at E. We also have a clockwise movement because of this UDL 200 force. We have plus 200 into the distance between the 200 force and the A, which will be until D it was 5.5. And 5.5 plus 2.5 will become 8, and then 9, and then 10. So it is total distance is 10. So total beam length will be 11. Yeah, total beam length is 11. So we have also an anti-clockwise movement because of FGY acting in the anti-clockwise direction. That is why we will give it as a negative, and the total distance is 11. So you can solve this equation and we will get the value of FGY from this equation. Let us calculate that. We have 800 plus 100, which is 900. So 900 plus 500 into 5.5 minus 1000 plus 2000 divided by 11, we have 422.7. So FGY becomes 422.7. So this is FGY. If you put this into your first equation, which was FAY plus FGY is 800, then you will get the value of FAY also. It will 377.2. So FAY will come out to be 377.2. It is for it 27, so it will be 3 because the total summation should become 800. So yeah, we have that. So we can just write our answer as FGY comes out to be 422.7 and FAY comes out to be 377.3. So we have found the support axis. Now we can just find the shear forces at every point. For that you need to follow like a sign convention. I will just tell you like what is the sign convention which we will follow. For the shear forces, if you are calculating the shear force at a particular cross section from the left side forces, considering all the forces on the left, then you need to consider upward forces as positive and downward forces as negative. And if you are considering forces on the right, then you need to consider upward forces as negative and downward forces as positive. So what I mean is like let us say you have a B, C something, and you are calculating force at B, shear force at B. Then you can either consider forces on the A side or on the C side. So if you are considering on the A side, it will become on the left side. So for the left side, we follow this sign convention, upward sign convention. So that is what I mean by left side forces and right side forces. So let us calculate shear force at A. Shear force at A will become the reaction at A, which is FAY, which is 377.3. And shear force at B, let us calculate shear force at B. We have 377.3 minus the UDL load, which is 100. So it becomes 277.3. We have shear force at C, same as shear force at B because there is no shear force in between. So it will become 277.3 only. We have shear force at left of D as 277.3, and shear force at right of D as 277.3 minus 500. So it will be minus 222.7. So why are we calculating left and right of a certain point? So whenever you have a certain force, let us say there is a certain force at point B of 500. So you need to consider left and right of that particular point. But if you have a sudden movement, let us say at C and E, then you need to consider this same condition for bending moment diagram. So you will calculate bending moment left of C and right of C. So whenever you have sudden force at a particular point, try to calculate left of that point and right of that point. At D, we have calculated right that because of that condition. It just helps us visualize how is the shear force varying at that particular point. So shear force at E will become the same, which is minus 222.7, because again there is no shear force between D and E. And shear force at F will again become minus 222.7. and shear force at left of G, let us say left of G, we have minus 222.7 minus 200 of this UDN, which will be minus 422.7. And at G, shear force at G, we have 422.7 reaction at G, and the shear force minus 422.7 at the left of the G. So we will just have zero shear force at G, because left of the G it is a minus 422.7, and at G there is a reaction of a positive 422.7. So that is why it comes out to be zero. Like it is also a great way to check if your shear forces values are correct, because at G it should come out to be zero. The shear force should come out to be zero. So let us draw the shear force diagram. As we have what the values, we have A, B, C, D, E, F, and G. These are the points which we have. At A, we have a shear force of 377.3. So 377.3. At B, we have 277.3. 277.3. At C, at D, same. So C will be same, D will be same. Just right of D, it is minus 220, minus 222.7. Which is same until F. And just left of G, it is minus 422.7. So minus 422.7. And at G, it is becoming 0. And the another concept which you need to understand is that whenever there is a UDL, the shear force will vary as an inclined line. And whenever there is not a UDL, then it will vary as a constant line, because the shear force is constant throughout. But whenever there is a UDL, it will vary like this, like an inclined line. So this is what your, this line should be straight line. So this is how your shear force diagram will vary throughout the beam. As you can see, we have been given this inclined line whenever there is a UDL. So yeah, the shear force diagram will be inclined line whenever there is a UDL, and the bending moment diagram will be an parabola, because bending moment is nothing but d shear force. Sorry, the shear force is nothing but the derivative of bending moment. So shear force will be nothing but derivative of bending moment. So if the shear force is of degree like an inclined line, so bending moment will be a parabola. And if the shear force is constant, the bending moment will be a linear line. You can like integrate this shear force, putting anything, like putting a constant, you will get a straight line, and putting a straight line, you will get a parabola. So this is how you can draw your shear force diagram. Let us move on to the bending moment diagram, for which we need to calculate bending moment at every point, and left and right of the point if there is a sudden movement at that particular point. Which in our case, we have a sudden movement at point C and E. So we have bending moment at A, A and G will become 0, because they are the extreme points, and at extreme points the bending moment always becomes 0 unless there is a fixed support. So in our case there is no fixed support, so bending moment at the extreme point will become 0 because of the equilibrium condition. You can also calculate it, it will come out to be 0 because of the equilibrium condition. And we have bending moment at V now. So yeah, I will quickly just explain the sign convention again for the bending moment one. This is for the shear force one. So for the bending moment, if you are considering forces on the left, then clockwise will become positive and anti-clockwise will become negative. And if you are considering forces on the right, then clockwise will become negative and anti-clockwise will become positive. I will just we'll just see how we can how we are doing this. So we have a bending moment at V, which we can calculate. So this is our cross section at V. We can calculate either from the forces on the left, which is the two forces, FAY and this 100 force because of the UDL. Or we can consider all of the forces on the right. We will not do that because it will just make it more complicated. So we will consider forces on the left. So on the left we have FAY, which is 377.3 into the 2, and it is a clockwise movement, so it will be positive, minus 100 into 1, and because of the UDL, and it is an anti-clockwise movement, so that is why it is a negative. So 377.3 into 2 minus 100, will give you 654.6 as the bending moment. We also have bending moment at left of C. So left of C, if you draw like a certain cross section here, you can again consider forces on the left, which will be nothing but 377.3 into the total distance is 3 now, minus 100 into the distance is 2. The only thing which you need to understand here is that whenever you're calculating, let us say bending moment at right of C now, right of C, so it will be the same 377.3 into 3 minus 100 into 2. Just that there will be an anti-clockwise moment of 800 you need to consider, because now let us see you are drawn here. So this 800 clockwise 800 moment which is applying suddenly at the C, you need to consider that also, which you did not do when you were calculating on the left of the C. But when you are considering right of the C and you are considering forces on the left, then you need to consider this moment, which is a positive 800 because it is a clockwise moment. So it will be positive 800. Yeah, this is just the concept which is important. So 377.3 into 3 minus 200 will give you 931.9 as the moment. If you add 800 to it, you will get 1731.9 as the moment. We also have bending moment at D, because there is no sudden moment, so we will not calculate left and right of that. We will just calculate at that particular point because there is no sudden. And let us consider force on the left again. We have 377.3 A2, 3 plus 2.5, which is 5.5, minus 100 into 2.5 plus 1 will become 4.5. And we also have a certain moment of 800 acting clockwise. So this is the total moment at D. We have 377.3 into 5.5 minus 450 plus 800. It comes out to be 2425.15. So this is also a great way to like check your bending moment values, that whenever there is a shear force value coming over to be 0, that this is shear force value 0 at, is coming like here at point D, then you know that the bending moment should be maximum at that point, because again it comes down to that shear force is dm by dx. So if the bending moment should be maximum, the shear force should be 0, because the slope at that point should be 0 of a curve. So the shear force should be 0 if the bending moment is maximum at any point. So firstly, we made the shear force diagram and we observed that it is 0 at point D. So we like know that bending moment should come out to be maximum at that point, let us say at T. And it is coming out to be maximum. So yeah, that is how you can check your values also. Bending moment, let us calculate at left of E. And bending moment at right of E. Left of E, you can consider forces on the right now, because it will be easy to consider forces on the right. Yeah. So we have, if you are calculating on the left of the, let us just take force on the left only, because if you, okay, you can also consider on the right. Okay, it is your like opinion, or if you find the right side to be easy, you can do that, or if you find the left side to be easy, because we have been doing that still now, then you can do it on the left side also. It is up to you. So let us consider now on the right side. You need to consider this moment also, because you are considering the right side force and you are calculating the bending moment at the left of the point. So firstly, you have 1000 anti-clockwise movement, and it is positive because it is on the right side and it is anti-clockwise. So if you look at your sign convention on the right and anti-clockwise, it comes out to be positive. And you also have a 200 force acting clockwise movement. So 200 into 2 clockwise movement is negative. And anti-clockwise movement of FGY into 3. So FGY is 422.7 into 3, and this anti-clockwise movement, so it is positive. Oh yeah. So this comes out to be 422.7 into 3 minus 400 will be 868.1. So we'll just write it somewhere here, 868.1, because we will need that value again when you are calculating bending moment at Okay, this is at right of the, this should be at left of the, and right of the we write it here. Yeah, this is at the left of the, and 868.1. So 1000 minus that is 131.9. And if you calculate the bending moment at right of the, you can neglect this anti-clockwise movement now. And considering force on the right again, we have minus 282 plus 422.7 into 3. So it will come out to be 868.1 as we have calculated earlier. Just remove this 1000 anti-clockwise movement. So we have bending moment at F also, which will be 200 into 1 clockwise. So minus 200 plus 422.7 into 2 because of the FGY force. 422.7 into 2 minus 200 is 645.4, and we have bending moment at G as 0. So we have calculated all the bending moments now. So let us just make the bending moment diagram quickly. We have this B, A, B, C, D, E, F, and G. At A, we have 0 bending moment. At B, we have 654.6. And at this left of C, we have 931.9. 931.9. Right of C, it becomes 1731. So 1731.9. Bending moment at T is 24. So let us say somewhere here 2425.15. We'll just separate this. Yeah. And we also have at left of the E, we have 131.9. So somewhere here 131.9. Bending moment at right of the E is 645.4. Sorry, 868.1. And right of the E it is 868.1. And we have bending moment at F as 645. So this is somewhere as 645.4, and G it is 0. So let us see how it is vary. We have and parabola between AB, because again it is a UDL. So shear force was linear and the bending moment will be a parabola. So this is a parabola. And BC it will be linear until it goes to left of the C. It was 931. So it is going to that, and then it is jumping. Then it is going this. Then at the left of the E, it was going to 131.9. So it will go to 131.9. Then it will jump to right of the E, which is 868.1. Okay. Something. Okay, 1000 minus, let us just calculate the ones again. We have 1000 minus 400, 600 plus 422.7 into 3, 1868.1. So this should be 1868.1. Yeah, sorry for this. We have left of the E as somewhere here 1868.1. So it should go to this. Then it will go to 868.1. And then at F, it is going to 645.4. Then again a parabola until G, it is going to 0. This is again a parabolic variation. So yeah, this is how you can make your bending moment diagram for the particular problem. Thank you.